Hi everybody. Today we're going to work on a little project to design and build an audio function generator which will provide the hobbyist with a variation of different waveforms, including a sine wave, square wave and a triangular waveform, and in addition to that I'll probably also include a ramp waveform and a variable pulse output waveform. The project will also have the feature of a digital readout to give an indication of the frequency, and the project itself will be in a format that will be easy for the hobbyist to make themselves. This project will be in two parts. The first part today we'll be looking at the design and build of the circuits and test it on a breadboard, and the second part we'll finalise the project and do a final build, box the unit and test it. So let's start now and have a look at the basic blocks of the design I'm proposing today. Right, well here we have an overview of our project today. I'll just go through briefly each of the sections of the project and then we'll look in more detail at each one. The power supply for the project will deliver both a 12 volt and 5 volt DC supply, and that will be derived from a 9 volt AC input. And that 9 volt AC input can either be supplied by a little mains transformer you could actually build on the project board, or if you're uncomfortable with working with mains supply, you can use a little mains adapter like this, which just plugs into the main supply and gives you 9 volt AC out on a little sort of plug at the end. So that's what I'm going to use today. It's obviously much safer as well, and maybe easier for the hobbyists. The important thing there is that if you use one of these little transformer modules, then you need to ensure that you get one which says AC out, not DC, AC out. Now the next section of the circuit here is the actual function generator part itself, and for that we're going to use a function generator IC which is manufactured by the XR Corporation, and we'll be using the XR2206 IC, which is a dedicated function generator chip which has been available now for quite some time, and you can pick these up quite cheaply on eBay today. Now this particular IC can be configured to a number of output configurations to provide either a square wave, a sine wave or a triangular wave, and it can even provide pulses or a ramp signal on the output if you wish. The frequency of the output is determined by a simple capacitor resistor network. The capacitor determines the frequency range and the resistor provides frequency tuning within that range. So that's the function generator IC here, and we'll be focusing on the frequency ranges between around 100 Hz all the way through to 30 kHz, although this IC can deliver higher frequencies than that. So we'll also maybe talk about how you can add higher frequencies if you wish at a later date. The output then from the function generator IC is then buffered by some FET operational amplifiers I'm proposing using, and what I probably will do is use a quad op amp in one chip package, which will be the TL084 IC, which is a quad FET op amplifier, and that will then give us the output of our signals in either sine, square, triangle, ramp or pulse, and we'll have some means of controlling the gain of the output as well. Now one other option I considered, which we may add, is having a separate TTL output which you could use when you're using digital circuits and you want a TTL 0 to 5 volt output signal. The bottom part of the circuit here today is all to do with delivering the frequency reading on the display, and for that we'll be using 8 7-segment displays, and that will be driven by the MAX 7219 IC, which is the 7-segment LED driver and multiplexer, and that particular IC is then driven on the SPI bus from the Arduino Nano, in which we'll not only have the software to control the LED display, but also we'll have the software in there to take the frequency input and convert that to a digital output. So in order to do that, we will be taking the square wave output from the function generator, feeding it through a buffer, probably something like a Schmidt trigger, and then feeding that into the Arduino Nano to then trigger the signal in there to give us the frequency reading output. So that's the basic circuit. One option that we could do is we could also put a switch in which will allow us to either use the frequency counter for the internal reading of the oscillator, or as an external output to measure frequencies external to the function generator. So that's the overview here of the project today. So let's have a look in more detail at each section. Right, here we have the power supply, which is quite straightforward really. We have the 9 volt AC coming in, and then going through a simple on-off switch and feeding a bridge rectifier, which can either be a small bridge rectifier of about 1 amp rating, or you can use 4 separate diodes such as the 1N4002. The output from the bridge rectifier circuit is then smooth with the 3300 microfarad, quite a large capacitor, and then we have some filter capacitors on either side of a 12 volt regulator, and that's the 78L12. It's a standard fixed 12 volt regulator IC, as is the 5 volt regulator IC. So the 12 volts is then smooth with the 100 microfarad, and we have our 12 volts out there. And then the 12 volt supply then feeds a 5 volt regulator that then simply gives a plus 5 volts out, which we'll use for the Arduino and for the logic IC circuitry. So there we have it. That's the basic power supply. Quite simple, quite straightforward. Right, well here we see the main element of our function generator circuit today, which is around the XR2206 IC. Now this particular IC has a number of elements built into it. One is it has a voltage control oscillator, it also has a current switch, and it has in addition to that a multiplier circuit and a sine wave shaping circuit. Now the voltage control oscillator part of this IC, the frequency of that is initially set by an external capacitor connected to pins 5 and 6 of the IC, and that sets the initial frequency band. As you'll see here, we have 2 capacitors. We have one capacitor which is permanently connected across pins 5 and 6, and we have another capacitor which I switch in with a simple single pole switch to give us another frequency band. Now you could actually have a rotary switch there if you wish, and switch in a number of different capacitors and give you some extra frequency bands, but in this case today we're going to concentrate on a frequency range from around 50 Hz all the way through to around 30 kHz. Within the frequency band, the actual frequency itself is then set by a timing resistor which is connected to pin 7 of this IC. So you have a 1K resistor there and a 100K pot, and by adjusting the 100K pot we can alter the frequency within that particular frequency band, so that will set the actual frequency. Once you've set the actual frequency, the frequency is coming out on pin 2, and on pin 2 we'll either get a sine wave or a triangular waveform coming out, and on pin 11 we'll have a square wave coming out with an equal amount to space ratio, and the peak to peak signal of that square wave will be the supply voltage, so it'll be 12 volts peak to peak, whereas the sine wave and the triangular waveform will be somewhere around 5 volts peak to peak. Now the circuitry here, which is the voltage control oscillator, the timing resistor which I mentioned here on pin 7, and the external capacitor, the charging of that is controlled internally with a voltage reference source. There is a 3.1 volt reference source inside this IC which is used, and that reference source is decoupled at pin 10 to ground via this 10 microfarad capacitor. Now the symmetry of the sine wave coming out is set by that preset there across pins 15 and 16, where the centre of the preset is going to ground through a 1K resistor, and we adjust that preset for symmetry of the sine wave coming out. And on pins 13 and 14 we have another preset resistor of 500 ohms, and that's used to tune the sine wave so that we can take out any harmonic distortion effects that you have upsetting the waveform and give you a clean sine wave coming out. So you adjust that preset there to give you a nice clean shaped sine wave signal coming out. If you switch that resistor out, then the output will go to a triangular form and you'll get a triangular waveform coming out. Now the signal coming out of pin 2, whether it be a sine wave or triangular wave, the peak-to-peak amplitude of those signals will be different. And for that reason, pin 3, where we set the output amplitude of the signal, I have two preset resistors there, and I have one which I'll set for the sine wave output, and I'll have another one which I'll set for the triangular waveform output. So as we switch the switch there between sine wave and triangular waveform, I'm also switching in a different preset to set the amplitude of the output signal. And in that way we can adjust these two trimmers so that both the sine wave and the triangular wave coming out are of equal amplitude. Now on pin 11 there, which I mentioned we have our square wave coming out at that frequency, I'm also tapping that off through a 1K resistor to feed that to our frequency counter circuitry on this project today, and I'll come back to that shortly. Now the other interesting feature with this IC, it not only has a timing resistor network here on pin 7, it has a second timing resistor network on pin 8, which is independent, and you can switch between the two. So I can either switch and use the timing resistor on pin 7, or I can use the timing resistor on pin 8. Now under normal operation we would just use the pin 7 timing input, but if you wanted to we could use pin 8, and to achieve the pin 8 feature I'm going to use pin 9. Now pin 9 is a input that allows us to switch between pin 7 and pin 8 for the timing resistor. So by feeding a signal onto pin 9, it will effectively toggle between pin 7 and pin 8 for the timing resistor. And as you'll see here, I'm taking the square wave output from the IC, feeding it back into pin 9 as a switch-in signal, and that's then going to switch between pin 7 and 8 continually. And I'm using that feature to give us our pulse waveform coming out here. So what you have here is a double pole switch. We throw that switch, it connects the additional timing resistor network in, and also connects pin 9 to pin 11. And now we have two timing networks, resistor networks here, and the signal going in on pin 9 is then switching between the two, and that's creating the pulse out. So that's our basic circuit today. What we'll do now is we'll build this circuit together with the power supply that I just illustrated earlier onto a breadboard, and we'll just test this first. Right, here you see we've laid out the circuit so far on the breadboard. So there's the power supply, 9 volt AC coming in to the bridge rectifier, the 3300 microfarad smoothing capacitor on the output of the bridge, and then there's the 12 volt regulator IC, the 78L12, the 2.1 capacitors either side, and the 100 microfarad smoothing on the output of the 12 volt regulator. So here we'll be getting 12 volts DC coming out, which I'll test before connecting it through to the rest of the circuit. On the remainder of the breadboard here we have the main function generator IC, the XR2206. There you have 200k linear pots, which we'll be using. That one there is the normal frequency control, and this one here we'll be using to alter the pulse width. The switch you see here is the one that we'll be using to switch the function of the generator from normal square wave to pulse mode. And the other switch on the other side here is the one we'll be using to switch between sine wave output and triangular wave output. And at the same time it connects in alternate gain controls for each waveform type. and that's to balance out any differences between the sine wave and the triangular waveform. The other two presets here, this particular one here is the one that we'll be using to alter the shape of the sine wave, and this one here is also affecting the sine wave symmetry and the shape of the sine wave. So these are used to trim and the original form of the waveform coming out. The output from the chip is coming from pins 2 and 11. Pin 2 we get normal sine wave and triangular waveform coming out, and pin 11 we have the square wave and the pulse waveform coming out. When we switch to pulse mode, we can also get a form of ramp waveform coming out of the normal sine wave output here at pin 2. These two capacitors here are the normal frequency timing capacitors. I've got two at the moment in parallel. There's a 0.022 and a 0.22. Normally we'd have a switch switching the larger value out of circuit, but for the purpose of testing on the breadboard I've just put them in parallel and I can remove one. So I think what we'll do next is we'll test the 12 volts from the voltage supply here, and if that's correct we'll connect to the rest of the circuit and we'll give it a test. I've just got the meter here connected to the 12 volt supply just to check that before I connect it through to the rest of the circuit there. I'll do that in a second. At the back there I've got the circuit that we've wired up so far on the breadboard, so that's the function generator IC and the little power supply circuit there with a 12 volt regulator. So we're going to check that 12 volts there first. And I've got the oscilloscope there connected to the sine wave output of the function generator chip. That's going to pin 2 there at the moment. So let me just check the 12 volt supply before I hook up the 12 volts to the rest of the circuit on the board. Okay, I've now switched the power on. I've got the 9 volt AC going in here, feeding the bridge rectifier, and we're now monitoring the 12 volt output, and as you can see there we're reading 12.16 volts on the meter, so that's fine. So what I'll do now is I'll just switch the power off again and then just connect the 12 volts through to the rest of the circuit and see whether it's functioning correctly. Right, I now have connected the 12 volts onto the 12 volt line here, feeding the rest of the circuit here. So let's now switch on. We'll still monitor the 12 volt out on the meter there, and we'll monitor now what's coming out on the oscilloscope, and also the frequency reading there is indicated on the scope as well. So let me switch the power on. Okay, there's the power on, and you can clearly see now we have a waveform coming out. So it's the sine wave coming out at the moment. So I've got the switches set into normal mode. So if I alter the control here now, we should be able to alter the frequency. So if I just try that. So at the moment I've got the two timing capacitors in there, and the frequency is going from a maximum of around 3.8 kilohertz. If I take it to the lowest frequency, it's going all the way down to about 40 hertz. Just switch the time base. So at the lowest frequency there, it's going down to just below 40 hertz, and the maximum frequency again is, step it up, is about just over 3.8 kilohertz. So that's with both the timing capacitors in there at the moment. So that's the sine wave coming out, and at the moment the peak to peak that are coming out, the oscilloscope is set to 1 volt per centimeter there on the scope, on the grid. So we've got 1, 2, 3, about 3.5 volts peak to peak coming out at the moment on the sine wave. So if I now switch this switch here, this will switch from the sine wave output to the triangular wave output, and at the same time it will switch over the gain preset for between sine and triangle. So let's just switch over and see if it works on the triangle for the moment. Well, there you are. Now one thing you'll notice there is that the amplitude of the triangular waveform is much larger than the sine wave. We'll just switch back to sine. You see there's quite a difference between the two, and that's the reason, under normal conditions, that's the way the circuit will normally work, and that's the reason I've actually put two little gain pots in here rather than just one. On normal circuits for this particular chip they seem to just use one little preset. What I've done here by using two and switching them in alternately, one for sine and one for triangular waveform, we can balance out the differences in the amplitude to get them more or less the same. Right, let me now adjust the triangular waveform amplitude control here to try and get that down to a similar level to the sine wave. So let's just try and adjust that and monitor on the oscilloscope. Now if I remember, we had about 3.5 volts peak to peak, so that's 1, 2, 3, probably somewhere around about there. So if I now switch back to sine wave, triangle, so you can see we've balanced the two out there. The other preset here, I can adjust the sine wave output as well, so I can increase that maybe a little bit. If you increase the so let's increase that to, if we increase it to somewhere there, which is round about 1, 2, 3, 4, 5 volts peak to peak at the moment. Switch back to the triangular waveform, just see if we can get 5 volt peak to peak on that one. Sometimes if you go too far it starts to cut off the peaks, so let's just see how far we can take it. So we've got 1, 2, 3, 4, just a bit more than 5. But if you go too high on that, I'll just demonstrate that. You'll see it's clipping now at the top. See how it's starting to clip. So let's take it back down to 5 volts peak to peak. So there we are, we've 1, 2, 3, 4, a little bit there. So that's reading now about 5 volts peak to peak. Switch back to the sine wave, and again we've there got 5 volts peak to peak. So what we've done now by trimming these two presets here is we've balanced out the differences between the amplitude of the triangular waveform and the sine waveform. So now when we switch over, the gain is the same for both. And that's really just a setup when you calibrate the unit to get them both to the same amplitude. Just try the frequency control. It's quite sensitive, the frequency control. We may later on have a look at a way of improving the controllability of this by having maybe an additional pot in series with this of a lower value to give you a fine and a coarse adjustment. Now what I'll do is I'm going to remove the larger of the two timing capacitors and just monitor the output waveform frequency. And normally we'd have a switch in here, but just for the purpose of the breadboard I'm just going to remove it. Well, immediately you see the frequency shot up there. It's now reading just over 17 kilohertz, but let's just see what the minimum frequency is this time. So take it down to minimum, and we have a minimum frequency there of 463 Hertz at the moment. And if we now increase it to its maximum, just alter the scope, and the maximum frequency there is currently reading 44.6 kilohertz. Now we might limit that on our circuit today to 30. Now I'll just demonstrate the effect of these two presets here, which affect the sine wave output. This one here affects the symmetry and the shape, and could affect clipping at the top, and this also affects the overall shape of the sine wave. So let me just demonstrate the effect of both of those. So this one here, which is the symmetry adjustment between pins 15 and 16, if I alter that, you'll see the effect it's having on the waveform there. You see how it's clipping at the top at the moment, so you need to adjust this to get a nice balanced sine wave there. If I take it too far the other way, you'll see that the effect it's having here. So you're trying to adjust the little preset here just to get some sort of a symmetry of your sine wave, somewhere around about there. And then the other preset here, this one is between pins 13 and 14, which is switched into position when you're on sine wave, but switched out of circuit when you're on triangular mode. So let's just see the effect of this one. See, again, you can see the overall effect of this. It's doing some clipping at the top, and you can see how it's affecting the shape of the waveform there. So again, you're adjusting this preset to get you the best quality sine wave coming out. Right, I've just put the other capacitor, timing capacitor, in there in parallel with the 0.022 there. So we're back to the original setting I had, and you see the sine wave we have out at the moment is at a frequency now of 3.84 kilohertz. You can alter that frequency by this particular control here. Let's just leave it at set it for probably around about a kilohertz or thereabouts. So we've set it about a kilohertz. I'll just alter the oscilloscope, and if I now switch the unit over to the square wave output by moving the oscilloscope now to the square wave output. So let's have a look at that. That's on pin 11, and you can see straight away that the amplitude of that is much greater. So let me just step that down. So we're getting an amplitude on the square wave output of the supply, really. It's 12 volts peak to peak coming out. So we may want to have a look at controlling that on the later circuitry of the function generator. But just for the moment, we have our square wave coming out, which is quite nice, and you can again alter the frequency of that by this control here. So this is now just simply altering the frequency of the square wave. So if I'll just leave it there. Now the other function I've added on this unit is the ability to get a pulse rather than a square wave. This is a 50-50 ratio duty cycle there. So this is an even on and even off cycle, but to get a pulse, that's why I've added the switch here, and I've got another control here which we can then alter the pulse width. So let me switch over to pulse mode. So we're now in pulse mode, and as you see, as I'm altering the this control here, it's altering the pulse width. Now if I go back to the sine wave output, one of the other features of having it switched into pulse mode with that switch is that you can get a form of ramp waveform coming out on the sine wave output there. So let's just have a look at that. And what you need to do there, I'll just connect that on, is you turn the normal frequency control fully clockwise. I'll just turn the gain up a little bit, and then by altering the pulse width control here, you can see we can vary the frequency of the ramp. Right, well here we have the frequency counter part of our project today. I'm simply going to use Arduino Nano and program that to act both as a frequency counter and then use it to drive a 8-digit 7-segment display. Now the 7-segment display module is itself driven by a MAX 7219 chip, which is controlled by the Arduino Nano. Now it's actually cheaper to buy the display module and the MAX 7219 chip as one module than to buy them as individual components. You can pick up these little modules quite cheaply these days on eBay, and everything is on one little printed circuit board with 5 connections that then just couple up to the Arduino Nano. The input into the Arduino Nano for that module is going on D10, D11 and D12, and the input for the frequency counter part from our function generator, the square wave signal from that, is fed into D5 of the Arduino Nano via a buffer, a Schmitt trigger buffer, this one here, which is part of a 74HC14 IC, just one element of that. We may be using some of the other buffers in that IC for other functions later. And I've also taken the opportunity to clamp the input of that signal to 5 volts by having a 5.1 volt Zener on the input of that square wave signal coming in. This whole circuitry here is also decoupled by a 0.1 capacitor. So what we'll do now is we'll build this up on a breadboard and then couple that up with the previous breadboard we had earlier with our function generator IC on. So let's go and have a look at that now. Right, here we now have the Arduino Nano. That's wired up to the 7-segment, the 8-digit display there, which has also got the MAX 7219 IC on there. On this breadboard here we also have the Schmitt trigger using one section of a 74HC14 chip there, and then the input of that is coming here to the square wave output from the function generator IC. Now the other thing I've done here is I've connected a current meter here to monitor the current, the input current from the bridge rectifier, just to monitor that, because I would suspect that as we drive the 7-segment display we'll start to draw a lot more current, and I just want to make sure that if there's any issues there, and for that reason I've also replaced the 12 volt regulator IC there with a 1 amp 12 volt regulator IC rather than the 100 milliamp one that I had there previously. I've also installed now a little 5 volt regulator there, and its associated circuitry, and again I may decide to change that to a 1 amp version, but we'll just try out that one first. So the first thing I want to do is I want to just check the 5 volts coming out before I connect it to the Arduino Nano. Right, I'll now switch on the power to the unit, and I just want to monitor the 5 volt supply on the meter there, and this one will be showing the current being drawn by the unit. So let me just switch on. So the circuit seems to be working okay. You've got our sine wave signal coming out. The current that's being drawn at the moment is just slightly over 27 milliamps, and you can see there on the meter on the right our 5 volt reading is reading 4.96, which is probably okay. So I think that's fine, and I can connect that up now to the Arduino Nano and circuitry here to drive the 7-segment displays. Right, I've now connected the 5 volt supply to the board with the Arduino Nano and the logic IC there, and I've changed the meter to monitor the 12 volt supply, which is feeding the function generator part of the circuitry, and this meter here is monitoring the current for the overall function generator, including the Nano now and the display. So let me switch on the power and just see what happens. Oops. Right, I switched on the power. You can see the Nano is working, and you can see that the display there is giving the frequency readout correctly, but unfortunately when we look at the display of the waveform there, you can see that there is some clipping and noise on the top of the sine wave, so clearly something's not right. The current now being drawn is 130 milliamps. That's probably the reason why we have an issue here. And when I look at the voltage now of the 12 volt supply, it's dropped right down to about 9 volts, and I think that is the issue we now have with the function generator part of the circuit. So I suspect the problem that we have is that the little mains adapter unit that we have to drive the 9 volts into this circuit here is not sufficient enough to supply both the function generator bit and the current required for the display and the Arduino Nano. So what I will do is I will use a different AC supply now to the unit here and just see whether we can resolve this problem. Right, I've now connected another AC supply input into the power supply circuitry here, and this time I'm using a 12 volt AC supply rather than the 9 volt supply I had earlier, and I'm now using a slightly larger unit, giving me a maximum I think of about 1 amp out. Clearly the unit we had before, which I'll just show you again, this little adapter here, this is only capable of supplying a few hundred milliamps, so I think really this was being overloaded, or at its top rating really, and couldn't handle the current. So I've replaced this now with a slightly larger one that can give up to 1 amp and gives us 12 volts out AC rather than the 9 volt that this one did. So now let me switch on the power with the 12 volts AC supply going in and just see if that solved the problem. Right, well, the function generator seems to be working fine. There's no noise now or clipping on the waveform. The frequency counter is working okay. The current being drawn now is around about 130, it's hovering, so around about 130 milliamps or so. And you can now see that our 12 volt supply is more or less spot on. It's 11.97, so that's back to more or less normal now, and I think that's the reason now why our function generator is working correctly. So I think the key there is to use a AC power supply to feed this that is capable of supplying 12 volts and a little bit more current than what we had previously, so probably around about 1 amp. You may even get away with 500 milliamp. Right, I've now just repositioned the display so we can see it more clearly while we're monitoring the oscilloscope and the frequency on the oscilloscope. So I'll switch on. You'll see the startup cycle as well on the display. It'll come up with, try to put Scullcom on there, and then it'll come up with the frequency counter. So let's switch on and let's have a look. Right, well, the frequency at the moment is reading 3,847 Hertz, and on the oscilloscope there we're getting 3,849 or 3,850 Hertz. So there's a slight discrepancy between the frequency on the oscilloscope and on the display, but we can actually correct that in software, which I'll show you later. Let me just try changing the frequency, and we'll monitor the display here and also the oscilloscope at the same time. I'm lowering the frequency, so we're now at a frequency of 345 Hertz, just alter the time base, and the oscilloscope is showing 346 Hertz, so there we've got 346 as well, 47, so it's pretty accurate really. Let me go down to the lowest setting, So I've gone right down now to hovering between 39 and 40 Hertz, and the oscilloscope is showing 39.47 Hertz. That seems to be working fine, so let's take it all the way up, and that's the maximum frequency with the two capacitors in, and that's reading 3847 Hertz, and the oscilloscope is showing 3850 Hertz. So again, it's just a few Hertz difference. Right, what I'll do now is I will take it down to the lowest frequency again, so back down at 39 Hertz, and I'm now going to remove the larger of the two capacitors. So now we're just using the small capacitor as the timing capacitor, and it's now reading 460 Hertz on the oscilloscope, and we're getting virtually the same there on our display. So if I now increase the frequency, so we're going up now, there we got 1.518, the oscilloscope showing 1.52 at the moment, and we've got 1519 on the display. So let's take it up. Right, we're now on 3512 Hertz, and the oscilloscope is indicating 3516 Hertz. So let's increase the frequency. Let's take it all the way up now to around 10 or 11 kilohertz. So the oscilloscope now showing 12.5 kilohertz, and the display here is more or less the same, 12,560 Hertz. So let's increase the frequency more. Right, 15, let's try a bit more. Right, we're at, that's interesting. The oscilloscope is now showing a frequency of 35 or 36,000 Hertz, and I'm not getting a correct reading on my display there. So let's just take it down and see when the reading comes back. What I'm finding is that I can alter the frequency to a maximum of 32,768 Hertz, and the display there works correctly. But once you get higher than that, the display stops, the frequency counter stops functioning. So I suspect that there's an issue with either the software or the way we're using the Arduino Nano to act as a frequency counter. But having said that, my intention was to make an audio type generator, function generator, going from around 50 Hertz to 30,000 Hertz. So in that respect it will probably work okay for our purposes, but we could have a look later at the software or to see if there's a way of getting the Arduino to read frequencies higher than 32,768 Hertz. Right, I've now connected a multi-turn 5K potentiometer in series with this 100K pot to give us a fine tune and use the 100K pot for a coarse tune. So if I now try adjusting the multi-turn 5K potentiometer here, we should have a more accurate control over the frequency. So let me try, and it's much better now to control. I've got more control over the frequency. Let me see. Right, we're probably now at the top end of the range of the frequency counter here. It's showing 32,697 or thereabouts Hertz. Certainly when I go anything over 32,768 it stops functioning, the counter. So that must be a function of the way we're using the Arduino Nano. It's probably something to do with the timer we're using in the Arduino Nano itself, not capable of going higher than that. But I think the multi-turn pot here, 5K in series with the 100K port is a good addition to give you more control over the frequency. Well, I hope you found that little project on designing and building a function generator of interest. In part 2 of this project I'll be covering the final build and the additional circuitry to do with the output amplifier stages. So thanks for watching. If you found it of interest, please give me a thumbs up, and I'll see you again soon with part 2. Bye for now.